Good morning, class. So today is October the 25th. Today I'm doing the lecture one day earlier. Today is the lecture for October 27th. And after I go through homework 6, it will be a review for the quiz, which is on Thursday, October 29th. So let's just get started on homework 6. Okay, so problem 1, you were supposed to figure out how much how much stored energy the tree adds to its mass every year. And I said to assume that the tree adds 100 kilograms of glucose to its mass every year, which, I don't know, sounds about right for a reasonably sized tree. So, photosynthesis is the chemical reaction where the plant takes carbon dioxide and water, 6H2O, and it makes glucose. Plus oxygen. So photosynthesis is basically like, like the chemical reaction burning alkanes backwards. I mean, burning glucose would be going in this direction, reacting with oxygen. The tree does it in the opposite direction and makes glucose using sunlight. And we're not going to get into the details of the physics of photosynthesis, but basically the light energy enables this reaction to proceed forward, even though you're storing chemical energy in the sense that there's going to, on this side, it's minus energy because that energy goes into the glucose molecule. Another way to think about it is that, okay, going in this direction, there's a minus energy on this side because that reaction takes energy to proceed. Sometimes, remember your chemistry, that's an endothermic reaction. Whereas if I went this way, if I then took the glucose and burned it in oxygen going that way, there would be a plus energy on this side. So you have to do the bond energy stuff again. So basically, for the glucose, there's 5 carbon-carbon, there's 7 CH, there's 1 COO, and 5 CO, single bond, and 5 OH. And then the oxygen, of course, there's 6 double O's here. And on the other side, there's of course 12 C double bond O, and of course the 12 OH. And so if you put this together, if you take this is on this side, oops, sorry. If you take this side, right, that works out to 158.1 EV, and on this side, that works out to 130.074 EV. And so, of course, as you see, the total bond energy on the right is now less than the total bond energy on the left, because basically you're producing potential energy. Things are less bonded on this side, and so you have stored energy in the potential energy of the glucose molecule. Now, someone asked me a question whether the stored energy was the bond energy of the glucose, and that's of course not true, because this is just like lifting something against gravity. Okay, I lift it against gravity, I have the potential energy, which is the difference of these two. Okay, it's like I go from this energy to this energy, and then that potential energy can be released by then burning the glucose in oxygen going in that direction, And so you recover the difference, okay? You don't recover what's in the glucose itself. So you have to take the difference, and so the stored energy is equal to the difference of these two, 28.026 eV per glucose molecule. All right, and the glucose molecule weighs, okay, an AMU times, okay, you have to add them up, so it's 6 times 12, sorry I'm running out of room here, plus 12, that's the hydrogens, plus 6 times 16, that's the oxygens. And so when you take that over that and you convert it to joules, and then the BTU, or no, you don't have to convert to BTU here. You convert that to that, you get that the stored energy is equal to 15 million joules per kilogram. And so 100 kilograms means that I've stored 1.5 billion joules per year. All right, so I mean, just taking 15 million times 100. That's the amount of stored energy in the tree's glucose every year. And you know, I asked you, and this was just kind of for fun, really. I mean, the main thing is to get that answer there. But the average power then is equal to 1.5 billion divided by the seconds in a year, 365 times 24 times 3600, and it works out to 47.6 watts, which I just thought was a fun thing to calculate. It means the tree, you know, there's one tree sitting there is on average generating 47.6 watts of fuel power, essentially, per unit time. So that's kind of neat. Now, that was just for fun, really, to do the watts, and so it sort of gives you an idea of what the tree is kind of doing the whole time. Now, 2 was to calculate what is the efficiency of the tree. And to do that, that's basically the stored chemical energy divided by the total sunlight energy okay, and we know we calculated the stored chemical energy in the first one. Yeah, 1.5 billion. Okay, and the total sunlight energy, you basically had to use, you know, I said assuming the leaf capture area is 10 square meters. Okay, so there's a very rough geometrical approximation and all that. But basically, then it's 10 times 1,000 watts per meter squared. Times 10 meters squared times, and then, you know, I'll just do this, the number of seconds in a year. Okay, and watts is joules per second, so that gives you joules. And that works out to 3%. So I mean, all the numbers in this problem were very rough and sort of made up, the 100 kilograms and things like that, and the 10 square meters. Sorry. Times 4.75. Here, let me write that out because that was an important point. The sunlight energy in 1 year. Okay, and so we went through this. So for every day, it's equal to the sun shining fully at 1,000 watts per meter squared for the state of Delaware for 4.75 hours each day. So the stored sunlight energy is 1,000 watts per meter squared times 10 meters squared gives you the watts on the tree, times, not that, sorry, times the number of hours in a day, times 365, times 3,600 seconds per hour. So it's not 24, it's 4.75, that's the whole point. And that works out to 5.26 times 10 to the 10 joules. So using 10 square meters as an effective capture area for the tree, which, I mean, you know, if that's right or not, you know, leaves and the geometry and stuff, that's the total sunlight energy that falls on the tree in the state of Delaware in 1 year, using 4.75 hours per day. And so you divide the stored chemical energy by the total sunlight energy, and the tree has been 3% efficient at converting that into stored chemical energy, which, you know, sounds about right, really. That a plant, a biological process, would have a few percent efficiency at taking whatever sunlight energy is falling upon it and converting it into useful stored chemical energy. And you know, that you can use that to sort of get an idea of comparing, you know, 3% for a tree versus 20% for a solar cell. You know, and it sort of fits in with problem 3 and homework 5, that, you know, you can get a lot more out of solar panels, but it's a much higher capital cost to put up the solar panels versus just planting trees. Okay, so that was homework 6, and now we're going to do the review for the quiz. And so what I'm going to do is I'm going to try and this is essentially after nuclear. And so we're gonna, I'm gonna try and section the board and so that I can leave up everything at the end. So we started covering solar generally. So I'll mark that 1. And that, you know, sort of started with that the sun at the Earth in space is at 1400 watts per meter squared. So that was just basically geometry. And then on Earth, 1,000 watts per meter squared after you get to the atmosphere. And additionally, we did the energy balance of the Earth, where, let me draw it over here. So here's the Earth, and here's the sun. And so up here in space, you have 1,400 watts per meter squared. And then when you get onto the Earth after, going through the atmosphere, on a clear day, you have 1,000 watts per meter squared. That's a very clear day. And we went through and explained how all this works, that you have sunlight energy or sunlight power, and you have the atmosphere, and then you have the Earth emitting infrared radiation. And some of that is captured in the atmosphere due to like CO2 and other things. And so you have what is finally Earth's IR radiation after going through atmosphere. And we basically, I showed you that the temperature of the Earth, T, adjusts itself so that this equals that, so that the Earth is in energy balance. So the amount of sunlight, now that's after reflection, of course, and I won't go through all the numbers here, but what I want you to instead understand is the general principle that the Earth's temperature adjusts itself so that the IR radiation that goes into space after being absorbed, whatever, in the atmosphere, equals the amount of sunlight radiation after reflection off the Earth that is captured by the Earth. That has to be in balance, and this doesn't change. Okay, not much. It changes a tiny little bit actually in the sun's cycle. But so basically, as there's more absorption in the atmosphere, okay, meaning less would get out into space, the Earth's temperature has to go up to make these arrows bigger. So that's climate change in a nutshell, basically. As there's more CO2 in the atmosphere, there's more absorption of this IR, so there's less that gets out into space. So to make it an energy balance with the sunlight, T has to go up. All right, so we then talked about wind and wind and solar have very large potential could be 100% of U.S. electricity. We walked through the numbers. For example, and their limit is their intermittent nature. That is, we went through that. Okay, if you go through the numbers for wind and of course for solar, there's plenty of resource. Okay, there's more resource than we can ever use, in fact. But the issue is that at any given spot on Earth, the sun doesn't always shine, the wind doesn't always blow, and so it's the fact that its intermittent nature limits it, which then, the remedy is, smart grid, or storage. And we went through and talked about, what percentage of electricity can be wind and solar before you have to start having smart grid type principles, and then at what point, this is basically somewhere around 25% or so, and this is sort of greater than 40%, something like that. I've been making up those numbers, they're very rough. Whereas right now we're at around 18% or something like that, and so we haven't run into these issues yet. And that was just sort of a general run up to solar, and then I'm running out of room here, but two, okay, we went over solar cells. And I won't go through all the physics again, but what we derived is the current voltage characteristic, IV, and this curve is given by I is equal to, now what I'm going to do, I'm going to put approximate here. This is for V is much bigger than KT, whereas KT is 0.026 volts. Okay, is approximately equal to A e to the negative EB minus EV over KT. That's the dark current. All right, EB minus EV is our barrier energy that is lowered when you apply voltage, minus IL, the light energy. And power is I times V. So it's 0 here and it's 0 here, so it's at a maximum there. And we also derived the open circuit voltage. From there, you can solve for that, and you get that this is EB over E minus KT logarithm of A over IL. KT over E. Where, remember when you take electron volts, EB is usually 1 electron volt, and so EB over E is around 1 volt. So we derived those things about solar cells, and so you can solve certain problems like we did in the homework of how VOC changes with energy. or changes with temperature. Um, and I left out one thing. I have to put up here 1A. Okay, so I'm disjointed a little bit here, but so we talked about solar energy generally, about what's going on the Earth, and how, the fact that there's this sort of almost infinite availability of wind and solar power, but how much of it we can use is limited by its intermittent nature. We went through and taught how solar cells work, NNP junctions and things like that, and derived this current versus voltage relationship. And from that, we derive things like the open circuit voltage and the fact that it goes down with temperature. And you can see here how it is affected by IL as well, that basically as IL goes up, sunlight energy goes up, the open circuit voltage would go up because that's in the denominator. And the quiz will be open book, and so you have all this information. I'm just going through generally the important points that we learned. Now 1A I forgot to put here was we learned about solar, and I'll call it insolation. It's a funny word. It basically means what we just did in the homework, that if you take actual sunlight, every morning gets a little stronger. If that's a cloudy day, that's a sunny day. Okay, this is solar watts per meter squared. That's equivalent to, okay, it coming on full strength for a certain number of hours every day. And T for Delaware is 4.75 hours. And you have those maps in the notes for, okay, now this is for, this is for a solar panel tilted at latitude facing south. And there's also maps for the solar panel laying flat. So clearly, how many hours that is equivalently every day depends upon, for example, if it was facing north, it'd be a lot less, right? So this is for facing south. And clearly, if you lay it flat, so let me draw this. Whereas if you lay it flat, that number of hours is going to be smaller. All right, so I just backing up there a little bit, and so we covered solar that way, both how the cells work, as well as how to calculate things from them using the principles of sunlight and things like that. And then 3, we get to biomass and biofuels, where there we covered primarily ethanol. We went through the ethanol. Okay, so we went through the biomass. There's currently no energy crops. And we went through, there's the potential for, greater than 50 quads per year. we went through that how, that if we did that, okay, to grow this 50 quads per year of biomass stored chemical energy, we'd have to input somewhere around 25 quads per year of additional electricity and diesel use for the tractors and everything else. And so actually this year I think I'm going to try and adjust the final project file so that if you increase the biomass above a certain level, see currently right now it's all waste. All right, and then for ethanol, we learned that yeast, okay, they take glucose. I won't write the chemical equation, and they digest it and make ethanol in the absence of oxygen plus CO2, and they get energy out of that. Because that's how they survive, and so the ethanol kind of has lower energy because it's a byproduct of an already digestive or energy releasing process. And we worked out that that's around I think it was 28,000. I should write down the right exact number here. If I didn't drop my papers. Okay, I'm going to write down a number, but if it's wrong, I think I remember 20,400 BTU per kilogram, compared to around 40, I think, again, it's 44,000 BTU per kilogram for gasoline. And we went through how currently most gasoline in the U.S. is 10% ethanol. But it can't really go much higher than that right now because most of the vehicles in the country can only tolerate 10% ethanol. You can buy a vehicle that can tolerate like 85% ethanol, but most cars in the U.S. can only tolerate 10%. And then, I'm getting my notes all glossed up anyway. Then basically we started on heat engines. And for purpose of the quiz, all I want you to remember then is we learned about the pressure volume diagram. P, V, and we started learning about, we're jumping ahead, and I don't want you to get too hung up on this for the quiz, but I want you to know this one particular principle. We started on the Carnot cycle, where basically the piston goes up, the volume goes up, and the pressure goes down, and it has these cycles, which we'll explain after the quiz. But basically, energy is equal to force times distance, so it's also equal to the integral of pressure PdV, because this is energy times distance for a piston and a cylinder. And so now the point is that volume going up, there's positive work done by the gas in the cylinder on the piston, and then for V going down, there's negative work done because then basically on the way down the the piston is doing work on the gas, and so you're losing energy to your crankshaft, and so the net energy is equal to the integral of PV for V going up minus the integral of PdV for V going down, and so it's the area enclosed there, because the integral is the area under the curve. So as it's going up, you're getting energy out, and that's the area under that curve. And then when you go back down, you have to subtract the area under this curve. All right, and so the net energy done is the area enclosed by the curve. And so we introduced the concept that the whole thing in engine design is to design this pressure volume process so that as the piston is going up and the volume is going up and the pressure is going down, okay, it traces a higher pressure curve. Then when it goes back down, the volume going down, you're compressing the gas, you have to set that up somehow so that that curve going back is going at a lower pressure, so that the net work done, there's actual net work done per cycle, which is the area between those curves. And that's it. That's the extent of our review. Look at this video, and then Tuesday when we have our chat session, we can talk about it and make any clarifications that are necessary. I've made up the quiz. The quiz is going to be, the same kind of thing, somewhere around 8 questions, and each question will be multiple choice. This quiz might be a little harder in the sense that you are going to have to maybe make a few calculations here and there. It won't just be like off the top of your head answering a question. Have a piece of paper handy to do some small calculations, or calculators or whatever. Of course, it's completely open book, so any formulas you will have access to. But there will be a few more little calculations in this quiz. All right, that's it. So I'll talk to you on Tuesday.